Deep Learning Explained. Neural networks and deep neural networks. Did you ever imagine a world driven by data, where information holds the key to unlocking endless possibilities, with a revolutionary technology emerging with deep learning? Sounds great, right? It is the power of deep learning. Welcome to our channel. In today's video, we will explain briefly what is deep learning. Together we'll also discuss neural networks and deep neural networks very clearly. Before we jump into today's video, we invite you to smash that subscribe button so that you won't miss any of our videos. So without further ado, let's get started. First, we like to ask you a simple question. Do you know or have any idea about deep learning? Any confusion? Yes, most of you are new to this topic. But you may think, how do we know about it and explain to you? You can keep your trust in us, as we are a team who does research regarding this deep learning. There's nothing special than learning from a team of experts. So, you are in the right place to explore what is deep learning. Now let's get an idea about what simply deep learning is. In our human brain also, we have multiple layers to perform complex tasks. Our brain is focused and trained to perform such tasks through feelings or experiences. So, how this factor combines with deep learning? Deep learning refers to a subset of machine learning techniques that focus on training artificial neural networks with multiple layers to perform complex tasks. Now, you may have a small idea regarding it. If not, we remind you to stay tuned till the end of this video to get the actual use of it. On our way, next, we'll talk about deep learning models. Unlike traditional machine learning algorithms, deep learning models can automatically learn hierarchical representations of data, enabling them to extract intricate patterns and make accurate predictions. Deep learning also enables machines to achieve human-level performance in challenging tasks such as image and speech recognition, natural language processing, and even autopilot driving. Also, deep learning has unlocked unprecedented possibilities for solving complex problems. So, get ready to explore the fundamental concepts and goals of deep learning now. As deep learning is an artificial neural network, it is inspired by the structure and functioning of the human brain. These networks consist of interconnected nodes called neurons, organized into layers that process and transform data. The depth of these networks, with multiple hidden layers, distinguishes deep neural networks from shallow ones. Now you may be wondering, what are these neural networks? Keep watching. We are on our way to exploring neural networks. Neural networks form the fundamental building blocks of deep learning. In this section, we will explore the structure and components of a neural network, including neurons, layers, and connections. We will also delve into the processors of ahead propagation and backpropagation, which are essential for training neural networks effectively. Neural networks are computational models inspired by interconnected neurons in the human brain. They are designed to learn from data and make decisions or predictions based on that learning. Neural networks consist of layers of interconnected nodes, referred to as neurons, which process and transform input data to produce output predictions or classifications. Neurons are the basic units of computation in a neural network. Each neuron receives input signals, performs a computation, and generates an output signal. The output of a neuron is normally handed through an activation function, which introduces nonlinearity and permits the community to learn complex patterns. Neural networks are organized into layers, which are stacked on top of each other. The input layer receives the raw data, and the output layer produces the closing predictions or classifications. In between, there can be one or extra hidden layers that perform intermediate computations. The number of hidden layers determines the depth of the neural network. Neurons in adjacent layers are connected by using connections or edges, which represent the flow of information. Each connection has a related weight that determines its energy or importance. These weights are discovered at some point in the education technique and play a crucial role in adjusting the network's behavior. Describing the system of ahead propagation and backpropagation for coaching neural networks. Forward propagation. Forward propagation refers to the process of feeding input data through the neural network, layer with the aid of layer, to produce an output prediction. Each neuron computes a weighted sum of its inputs, applies an activation function, and passes the result to the next layer. This process continues until the output layer produces the last prediction. Backpropagation. Backpropagation is the key process for learning neural networks. It involves computing the gradients of the network's parameters, weights and biases, regarding a loss function that quantifies the network's performance. These gradients point out the course and magnitude of changes wished to limit the loss. During backpropagation, the gradients are propagated backward via the network, layer by using layer, with the use of the chain rule of calculus. The weights and biases are then up to date with the usage of optimization algorithms like gradient descent, which iteratively alter the parameters to minimize the loss function. By repeating the forward propagation and backpropagation method over a large dataset, neural networks can research to make accurate predictions and improve their overall performance on various tasks. Understanding the structure and functioning of neural networks, along with the training processors of forward propagation and backpropagation, varieties the basis for efficaciously utilizing deep getting-to-know techniques. Next, we'll explore the training procedure of neural networks. Training neural networks involve crucial components and techniques that enable the networks to learn from data and improve their performance. In this section, we will explore the importance of data and labels in coaching neural networks, talk about the position of optimization algorithms like gradient descent, and introduce ideas such as loss functions, activation functions, and regularization strategies to enhance network performance. Training neural networks require a significant amount of labeled data. Labeled information consists of input samples paired with corresponding target outputs or labels. The network learns from this labeled data by adjusting its parameters to limit the discrepancy between its predicted outputs and true labels. The quality, diversity, and size of the training dataset play an integral position in the network's ability to generalize nicely and make accurate predictions on unseen data. Optimization algorithms play an important role in training neural networks using iteratively adjusting the network's parameters to minimize a loss function. One commonly used optimization algorithm is gradient descent. It calculates the gradients of the loss feature concerning the network's parameters and updates the parameters in the direction opposite to the gradient, efficiently descending toward a minimum loss. Variants of gradient descent, such as stochastic gradient descent and mini-batch gradient descent, are often employed to efficiently handle large datasets. These algorithms stabilize the trade-off between computation time and accuracy, making training feasible even with vast amounts of data. Loss functions quantify the discrepancy between the predicted outputs of the neural network and the true labels. Common loss functions include mean squared error for regression problems and categorical cross-entropy for classification problems. The desire for the loss functions depends on the nature of the task and the desired behavior of the network. Activation functions introduce nonlinearity to the output of individual neurons, enabling neural networks to learn complex patterns and relationships. Popular activation functions include the sigmoid function, hyperbolic tangent function, and rectified linear unit function. Each activation characteristic has different traits and affects the network's learning capabilities. Regularization techniques are used to stop overfitting, which occurs when a neural network turns overly specialized to the education facts and performs poorly on new, unseen data. Techniques like L1 and L2 regularization add penalty terms to the loss function, encouraging the network to favor simpler weight configurations and reduce the influence of beside-the-point features. Other regularization techniques, such as dropout and early stopping, also help combat overfitting by way of introducing randomness and stopping training early when overall performance on validation data starts to degrade. By carefully selecting appropriate loss functions, activation functions, and regularization techniques, neural networks can enhance their generalization capabilities and achieve better performance on a wide range of tasks. Now, you're all caught up. We hope now you have an idea about the deep learning, neural networks, and deep neural networks we presented today through this video. You are warmly invited to argue your thoughts regarding our explanation in the comments section below. If you find this video useful and helpful for you, give it a thumbs up and share it with your fellow tech explorers. Until next time, keep exploring and keep updated on the ever-evolving technology.